Okay, so we're going to talk about free fall and its implications. What does it take for a tall building to collapse down through its own structure at absolute free fall? And also, what does it take for a building to collapse down at what I call near free fall, but what I'm talking about really is when it's collapsing at uniform acceleration, even if it's not at free fall. There's implications even there. And so those two conditions describe what happened to the various buildings on 9/11. And the other question is, what does it mean for a government agency, NIST, to cover up this fact? Why would they want to cover up what's happening? So that's part of this question. Okay, so this is going to be based on a series of articles I published at medium.com. One way to find this is you go to medium.com, but then it's hard to search in their search engine. You have to put my name and freefall, or you'll never find it. But the other way to find it is to go to my website, 911speakout.org, and it's a link right off the bat. It's right at the top of the page there. So a little bit of clarification. I'll be talking about NIST. It stands for the National Institute of Standards and Technology. People in this town probably know what NIST is because it's down the road. There's one branch in Gaithersburg, Maryland, and the other here in Boulder, Colorado. An important point about NIST is it's a government agency. It's in the Commerce Department under the control of the executive branch of government. So it's important to keep that in mind. When they were tasked with explaining what happened on 9/11, it's not as though they were simply an independent outside agency. It's an agency that was in the direct line of control from the executive branch of the government. I'm going to be talking about the World Trade Center, just the abbreviations. WTC stands for World Trade Center in my usage tonight. And it's a complex of 7 buildings, or it was. 1 and 2 are the North and South Towers, and Building 7 is the one that also fell precipitously on the same day without being hit by a plane. Now, the one here in the bottom right is Building 7, and it looks small by comparison with the Twin Towers, but it's only because it's in comparison with the Twin Towers. It's about the size, it's almost the size of the largest building in Denver. So there's I think a 50-something, 53-story building in Denver. This was for, huh?
Optiv. I believe it's the Optiv building.
Optiv building?
Optiv, yeah.
Optiv, I don't know. I'm new to Denver, but,
Yeah.
okay. Well, in any case, it's about 50-ish floors. This was 47 floors. So that's the size building we're talking about. It had a footprint that would cover a football field. In fact, I have an illustration later in the slideshow where I want to make that point a little bit more clearly. So this is the layout of what has become known as Ground Zero. There are several other smaller buildings there as well. I'm going to be talking about the fact of free fall and near free fall. Building 7, I'm going to show you, came down at absolute free fall for 2.5 seconds. The North Tower came down in uniform downward acceleration the entire time the roof line was visible. It was accelerating downward, and I'll show you some of the implications of that. It was not free fall, but it's what I'm going to call near free fall. The South Tower, interestingly, the top section fell off, but the building fell down anyway. So the thing that was supposedly driving the building down wasn't even there. It fell off early in the collapse, and the rest of the building just collapsed to nothing, or very little anyway. Okay, let's start by looking at each of these. The South Tower was the second building hit by a plane, but it was the first one to collapse. It lasted 56 minutes after impact, and then here's what happened.
So they're gonna need people to help.
Whoa.
Oh my God! Holy fuck! The tower just fell down.
Now this is the same building, just going back a little bit, just a minute or two before the collapse. lot in that little series of video clips. I could rewind it several times and spend the whole evening right there. Notice the top section fell off. Notice molten metal pouring out right near where the break point occurred. The color of the molten metal indicates the temperature, and it's the color temperature of molten iron or molten steel. People who tried to assert that this was molten aluminum at a lower temperature, like from the plane or something like that, that's a lame attempt at a rationale. The problem is you have a lower temperature, you don't get that color. And if you ever melt aluminum, you'll see it silvery in daylight. And so the color itself tells you it's at the temperature of molten iron. I'm going to keep on going. The North Tower, this is just a quick overview here. The North Tower was the first building hit, but it lasted an hour and 43 minutes before it came down. And here is a little composite showing some views of the North Tower coming down.
There have been frantic efforts to get people out of the tower. Now this is tape, and you can see now whether that was an explosion or exactly what happened that caused that second tower to collapse. We cannot tell you.
Look how broad
CNN's
that's
Kelly
going.
Wallace is on the phone with us. Kelly, where are you? What can you tell us?
Second building collapsed while we were on the FDR walking north.
Look at the ejections coming out the side, way down here, many floors below where the presumed cutoff point was.
Or did you think there was more to come?
So there's, again, many things to look for there. I've discussed all of these in various contexts. I'll be talking a little bit about some of these things tonight, but there's a lot to be untangled in these videos. Now, Building 7 came down at 5:20 that evening. It was not hit by a plane. And there was a lot of indication that people knew it was going to come down, even though when NIST analyzed how it fell, it was in a completely, NIST's account, or NIST's account of how it fell, it's a completely unique, unprecedented mechanism. So the idea that people somehow knew it was going to come down, there's no basis for that. So one must ask the question, how did people know it was going to come down?
The second building collapses. It came back 20 minutes later, looking like a Three Stooges movie covered in plastic, I swear to God. But you get a good thing, man. That's some good shit. Then we went back there. Whoa!
Now, here we're going to show you a videotape of the collapse itself.
Describe that.
Now we go to videotape, the collapse of this building.
It's amazing.
All right, let's come to some of the research I've done on this personally, which is doing some simple measurements to try and get a handle on what we're looking at. And so let's start by, we need to talk about what is acceleration. So let's start with a simple case of a soccer ball. Okay, here's a little demonstration of a measuring tool I use called Tracker. What I can do is take a video clip. I can take an object that's going to move, and I can put a mark on the object, and then I can track that. If I go single step here, notice what's happening. You're seeing the motion frame by frame. Over here, you're seeing a little mark that travels along the graph. And what this graph is showing is y versus t. So y is the vertical position, and t is time. Let's bring this back to the top. So if I just run it, I have a point for each position of the ball over here. Now we don't have to just track position. If I click on this, another thing that's useful is to track velocity. In fact, it says v sub y. This is the vertical component of the velocity, how fast it's moving downward as a function of time. So let's come back. So here, if I drop the ball, notice it's the same motion as before, but I'm not plotting where it is. I'm plotting how fast it's going at every second. Okay, so let's retrace our steps, and let's single step it for a while. And so, for instance, at this moment, it's moving downward at 2 meters per second. It's right here, but it's going 2 meters per second. If I step some more, at this point it's going 3 meters per second. Here's going 4 meters per second. Here's going 5 meters per second, and so forth. Now, this straight line graph is an indicator of uniform acceleration. The slope of the graph indicates how fast it's accelerating. If it's a steeper graph, it means it's picking up speed faster. That would be a faster acceleration. So let's right-click on this graph and click Analyze. And that brings us to this other tool called the Data tool. So if I click here and say Curve Fit, notice that blue line is on there. And if I select a range of data points, I can get the best calculated slope through those data points. Now notice at the beginning, it's not uniform. I'm holding it here. Then I let go, and there's a little transition as I'm letting go. So let's take some of these data points down here. So if I go, like, for instance, from here to there, notice that that blue line fits right along these data points very nicely. Down here it gives the equation of the line. Over here, the slope of the line is given by the value a. And notice that slope is minus 9.801. So that's very close to the acceleration of gravity. So this is the particular slope that indicates the acceleration of gravity. So if we look at any graph of velocity versus time, and it's a straight line graph, that indicates uniform acceleration. If we measure the slope, that gives us the actual acceleration. And if the slope is equal to 9.8 meters per second squared in a downward direction, that indicates it's in free fall. So that's just by way of background. You can understand a dropping soccer ball. And so this is what the velocity versus time graph looks like for something that's a simple, understandable motion. So what we're going to do is compare this with some building collapse graphs, okay? So let's start with a known, truly gravitationally driven building collapse. And there's a technique used in France called the Vernage technique for doing building demolitions that does not involve explosives. And I'll just let this explain itself, and if there's any loose ends, I'll tell about it afterwards. Okay, this is not the World Trade Center. This is a building in France, and they use a technique there they developed called the Vernage technique. And so instead of using explosives to demolish a building, they take a couple of floors out of the center here. They've weakened it. They've taken everything except the last little bit of support, and they've removed that. What they're then going to do, notice these little diagonal things here. Those are hydraulic devices. They're going to buckle these columns. And when they buckle the columns, they're going to allow this thing to drop. And when it drops, it's going to go through a little distance here where it's essentially without resistance, and then it's going to crash into the lower part of the building. And the top part of the building will then demolish the bottom part of the building. Of course, the bottom is exerting an equal force upward, so the two halves demolish each other at the same time. Let's see how that works. So if I run it here, here's the graph on the right. It's going along, nothing happening, and then finally, boom, notice it collapses. And there's a short period here where it's accelerating downward, and then it's actually decelerating where it's hitting over here. Okay. This time I'm going to stop it when it gets over here, and we're going to single step for a while. Okay, now here's where the building is going to start to buckle in the middle. So let's just go single step and watch that buckling motion. Notice how they've started the buckling, and once those things buckle, they offer very little resistance. This is not a calibrated measurement. I don't have the exact floor spacing or anything else here in this building. We just know it's accelerating downward very steeply. And notice that it's almost done accelerating downward, and this is going to very quickly here engage. And now notice all the dust showing that it's now fully engaged, and look where we are. We're down here at the bottom of this acceleration. As soon as it fully engages, this is turning around and actually slowing down. And so this is going to decelerate from the point that the two sections engage with each other. And notice that they're demolishing both halves of the building simultaneously there. And there you go. So the point is, as soon as this building engages with this part of the building, the free fall or near free fall, whatever this is, stops, and it actually starts decelerating. This is what you'd expect if the top section of the North Tower, for instance, actually crashed into the bottom section like they say it did and acted like a pile driver crushing anything. If this thing is able to use some of its energy to crush what's below it, it's going to not be able to continually pick up speed. It's going to actually slow down. And so this last little bit here where it's actually the graph goes upward means it's slowing down, and that's because the energy is getting used for crushing rather than continuing to increase the downward speed. Okay, those were all like typical illustrations. Let's see what happens in the case of the North Tower. In the North Tower, there was about a dozen floors that were falling down on top of the remaining floors. And according to the model used by NIST, the top section, they adopted what's called a pile driver theory, where it actually, you have to crush the columns underneath it. We'll get more to the structure of the building in a minute. But you have to crush the columns in order to get the building to come down. You can't just eliminate the floors. That would leave the central core of the building untouched. So let's look at this, and then notice in particular the way the graph looks for the North Tower. Okay, here I'm going to track two different points on the North Tower of the World Trade Center, also known as WTC-1, World Trade Center number 1. This point, the red one, which is indicated over here as a graph, this is going to track the roof line, and the green point up here is going to track this mark on the mast that's on top of the tower. So first of all, let's just run it. And notice what's happening here is these 2 points are tracking. Let's do it again. This time I'm going to come over here to mast B, so now it's tracking this one. Notice over here, as I start it, there's a little marker that goes down here along with each frame. So it's showing you as it's progressing on the picture, you're seeing how it's progressing on the graph. Okay, so we're basically tracking the vertical velocity as a function of time, and so in other words, it's coming downward because it's a negative, it's a downward velocity. So in other words, it's picking up speed at a uniformly increasing rate, because if it's going this fast, then it's going faster, then it's going faster. It's showing that the speed is increasing downward as time goes on. I'm going to cut that one off a little bit early, but the point to notice here is, notice that in the case of the Vernage demolition that we saw, it came down while it was actually falling with no interaction. And once the interaction began, the graph literally turned around, which indicated that the speed was now decreasing. So in other words, when you actually have interaction, it's going to turn the graph around. In the North Tower, it never turned around. And so we need to ask, what does that mean? How can you have what supposedly is a pile driver, and yet we know that the interaction should produce a deceleration, but there's no deceleration. So we'll look a little further into what that means. This is a pile driver. I put this in because the last time I gave a talk, somebody in the audience said, "What's a pile driver?" That's a pile driver. It's like a big hunkin' hammer, and they're driving piles, like pilings for a pier. That's where it gets its name. So you can drive like a telephone pole thing straight into the ground just by hitting it with a hammer, essentially. Multi-ton hammer here, okay? So, but notice something about the pile driver. It comes down and it's driving the post into the ground, but the post is decelerating the pile driver. In fact, it brings it to rest. So they have to lift it up and do it again, and over again, right? So it's the essence of this pile driver that it has to be a repetitive thing, because every time it comes down, it loses its momentum. It transfers that momentum into an impulse, if you want to use the physics terms and all that. And so by actually creating that excess force that you get, it's, that's what makes it act like this hammer, okay? Now, I'm going to, what?
I was curious, because the French building, that's mostly concrete and rebar. And then this one would have been steel. So I was curious as the differences between them and what
The physics is the same.
Correct. I was just curious what the Twin Towers were at that top level.
The Twin Towers, all of the vertical structure is steel. There's no concrete in the Twin Towers except for the floors. So they have basically steel columns. You have floor pans on each floor with 4 inches of concrete. That's the only concrete in the building. Okay. So you have a steel frame structure, okay? So here's an illustration. By the way, it was hard for us to figure out the structure of the Twin Towers at first because we were fed disinformation. The public didn't have access to inside scoop on this. So watch what we were shown at first. This was from Nova on why the towers fell, and look at the way the columns are illustrated there, like strings of spaghetti, like freestanding individual columns, and if you collapse the floors out, these things would just be flopping around and would come falling down. But look what it really looked like. It was a very massive set of columns through the core. That illustrates the size by a guy standing there. But these columns were interconnected. So that's the inner core columns there in the background of this guy that's on the structure. These were not flimsy columns. This would be a building within a building. If the floors came down, you would leave that inner structure still intact. And so the problem of how do you bring the towers down is how do you crush or cause to buckle or cause to somehow go away this inner structure. Now there's one thing I cut off that other video short a little bit with the red and the green dots on the North Tower. One of the things I did a little further on that one, it was just taking too long. But the green dot is showing when the mast, that was the television antenna on top of the building, when that started down, you can actually compare when the two started. The roof line versus the mast. Guess what? The mast started down before the roof line started down. The mast is right over the center of the building. The center of the building has these 47 core columns, which I'm going to illustrate in the next little video clip here again. And they had a little hat truss on top. Let's see that, and then we can keep talking. So here is a little animation showing the structure of the building. There's the core structure. This animation was created for one of the lawsuits, I think the insurance claims. But so there's the perimeter columns. The perimeter columns primarily were there to take wind load. The core columns, it's a very structurally stable, massive thing on its own. Here's the hat truss on top. And that tied the 47 core columns together and tied the core to the perimeter. And here are the concrete floors. So the concrete in the building is there on those floor pans, and that's it. Okay? By the way, there were no floor pans found in the rubble pile. Not a single floor pan survived the collapse. And if you just had a pancaking collapse of floors, you would expect to find pancakes. Here is a model that was constructed by a prominent structural engineer, Zdeněk Bazant, 2 days after 9/11. This was published, Journal of Engineering Mechanics, I think it is. I'm not keeping track on here. Yeah, Journal of Engineering Mechanics. And this is his explanation for how the tower came down. And he's taking into account, he recognizes that the issue is not pancaking the floors. The issue is, how do you crush the core columns? How do you cause them to buckle, to fail, for this tower to come down? So what he's saying is that initially you have the plane, it weakens some things, you got some fires going, or whatever's happening. He just somehow waves his hand and says, okay, let's assume you have 2 floors of free fall to get this started, and then calculates the impact, and he does some other figuring on the structure and so forth. And then he assumes that this entire top section crushes down the lower section all the way to the rubble pile on the ground. And once it gets down to the bottom, it then crushes itself, which sort of, we've seen an example of when 2 building parts collide in the French demolition. They demolish each other simultaneously. What I would expect would be, if this type of thing were happening, say there was a dozen floors above the break, it would maybe demolish a dozen floors, by which time the top part was demolished as well, leaving nothing to produce a coherent force to crush the rest of the building. You just have rubble at that point, rather than something that could hold together like a hammerhead or something. So this has undergone a lot of criticism. A lot of the criticism that our guys have done the analysis on this, it's extremely hard to get a critique of this published. The journal that published this, which is a blatantly flawed model, will not publish critiques of this. And so architects and engineers for 9/11 Truth. Tony Zambodi is one of the, he's one of several who has done a lot of analysis of Bazant's work. And he's done it at the forces on the individual girders and that kind of thing level. I've done an analysis of this that's on a more global level, which I'll be showing you in a second here. Okay, so I said, remember when we saw the top section coming down and it was accelerating downward? I guess one part I didn't go far enough. If you actually measure the slope of that graph, it turns out the top section of the building is coming down with an acceleration about 2/3 of g, 2/3 of the acceleration of gravity. So I thought, it's not in free fall. It's coming down at 2/3 of the acceleration of gravity. What does that mean? What are the consequences of that? So let me just try to illustrate that. That little arrow in the middle there is the acceleration. It's coming down at about 2/3, around 64% roughly, of g. So the force acting on the top section over here must be about 2/3 of the force of gravity. But there's basically 2 forces at work. You have gravity and resistance, right? So you combine the 2 and it has to come out to 2/3. So the upward force, that resistive force there, must be about 1/3. I did it all more analytically, but this is just explaining it hand-wavingly. But so the upward force that cancels the part of the gravitational force there is about 1/3 of the acceleration of gravity. About 1/3 of the force of gravity, which is, you call that the weight. So the upward force is about 1/3 of the weight of that block. Now you come back over here, and Newton's third law says two objects interacting, the forces are going to be equal and opposite. So if the bottom section is pushing upward on the top section with 1/3 of its weight, the top section is pushing down on the bottom section with 1/3 of its weight. They're equal and opposite. But look at that. That top section has been pushing downward on the bottom section for decades with its full weight, 100% of its full weight, and it has not caused it to fail. So how is it that all of a sudden 1/3 of its weight is not being supported? So in other words, normally if you were to take an anvil and drop it on your toe, it's going to hurt a lot more than if you take that same anvil and set it on your toe, right? In other words, the force that a falling object exerts on something, you would expect, exerts a force that's over and above its own weight. That excess force, and engineers call it a dynamic load, that excess force, us physics guys just say, well, what you're doing is you're taking momentum, and a change in momentum gives you a force. And so you have this excess force is caused by the momentum of this object coming down. You give up the momentum, and instead you get this force. Okay? But you have to give up momentum to get that excess force. And what's happening if this block is uniformly accelerating? It's never giving up any momentum. It's increasing its downward speed, so it's increasing its downward momentum the entire time. It never gives up a momentum, therefore it never delivers a dynamic load, and it exerts a force on this building that's less than its own weight. Now that's really hard to wrap your mind around. I have the math here if you want to see that version of it. Okay, so you'd think that a falling block would exert a force on the lower section larger than its weight, the dynamic load, but as we've seen, the fact the top block is accelerating downward implies the force between the two sections is less than its weight. How can this be? I'm a physics teacher. Here's a block of wood, here's a hammer. Now, if I set the hammer on the nail, notice it's not going anywhere, right? How do you drive the nail into the wood? You need to lift it up and give it some speed. And what you're doing is you're giving the hammerhead momentum. And what happens? What happened to the hammerhead when it hit? It stopped it, just like that pile driver, you know? It delivered the impulse, and in the process of it giving that extra force to the nail was stopping the hammerhead. How could you ever have a hammerhead that drives a nail without ever losing momentum? Well, if it never loses momentum, it's never creating a dynamic load here, right? So the reason this thing, the reason that doesn't drive it, but that does a little bit, is because I'm taking momentum that I'm cashing in for impulse, or this force. So, can you imagine a situation where you can have acceleration right through the impact? Well, I can. All right, here's a piece of styrofoam. Now, if I hit the styrofoam, well, by the way, the head of the hammer pushes it in. So if I bring it back out, all right, so what we're seeing here is the weight of the hammer by itself is able to drive this nail in, and that's the criterion. If you have resistance that's so weak that the weight by itself will drive it in, then if I hit it, it can accelerate the whole time. All right? So in order for a hammer to drive a nail and get acceleration through the whole interaction, the interaction has to be so weak, the resistance has to be so weak that it could have driven it without even any momentum at all, right? And that's why we're saying we saw that the force of interaction was less than the weight of the hammerhead. So that's pretty amazing. So what does that tell us about the North Tower? If the top section is accelerating downward through the impact, it's not much of an impact, is it? So it's telling you that what's underneath has been pre-pulverized, and it's not crushing anything, it's falling into pre-pulverized material. So that's proof right there that something other than the falling mass is what destroyed the tower. It had to have been pulverized ahead of the falling material. So when we say we can prove that there were explosives, it's because of that. And this is one of the proofs. By the way, I'm just taking one little tiny piece of evidence here, the motion of the building, the free fall or the near free fall. There's lots of other kinds of evidence that others in the scientist group and in the architects and engineers group have looked at. There's a good paper on the thermite, the nanothermite, that was found in the dust. There's evidence on all kinds of levels. Of course, you can go to other levels of research where they're looking at what was going on in terms of insider trading, evidence of foreknowledge. There's all kinds of ways that this stuff has been investigated. I'm just looking at the physics, because that's who I am. But it has implications that goes far beyond just the physics. Okay, so for the North Tower, WTC1, since the top section of the tower is accelerating downward with uniform acceleration, 64% of the acceleration of gravity, the structure, which previously could support 3 to 5 times the weight of the top block, the core section was designed to support 3 times its weight, 3 times the weight of everything above it. So at every level in the building, the core was capable of supporting 3 times the load above it. The perimeter columns were capable of supporting 5 times the load above it. So between the two, somewhere, a number between 3 and 5. And now all of a sudden it's failing to support roughly a third of the weight. It means about 90%, going from 3 to a third, that's where I'm figuring here. It's about 90% of the structure of the building has to have been removed to allow this collapse to occur. So it cannot be the top section falling that's somehow crushing what's under it. Let's move to the remaining building, WTC7. I found that it fell for 2.5 seconds at actual free fall. Not just uniform acceleration, but a particular uniform acceleration. And I'll actually show you the measurement here. NIST denied it. So in their final draft of their report in 2008, their final draft for public comment, which came out in August of 2008, they denied free fall. Then we piled on. I took my data, and other people brought in their argumentation, and we actually got NIST to backtrack. So they denied it, then they confirmed it. They came up with a graph that matched mine, almost. But they continued to deny its implications. We'll see this as we go along. Okay, in their final draft for public comment, they claimed it was coming down 40% slower than free fall time, as though that means anything. I mean, just the construction of the phrase, free fall time. You don't characterize free fall by a time. You characterize free fall by an acceleration. So this is weird, and it sounds weirder to my ears than yours probably, because I know what they should have said to make it make sense. This doesn't make sense. Okay, but it comes out of their methodology. It's as though they took a stopwatch. Their methodology was to measure a starting and stopping time, and they plugged it into this formula. Now, if you don't recognize how to turn this around in your head algebraically, in physics in high school, you learn a little formula that the distance is 1/2 gt squared. Turn that around and solve it for time, and you get this formula. So it's a simple little formula. But this formula has a built-in assumption, a couple built-in assumptions. It has to be motion starting from rest at uniform acceleration. This is valid only in the case of initial velocity is 0 and a uniform acceleration. So NIST time for WTC7 to fall, they timed it for 18 floors, which is what they could see above the foreground roofs they were looking at. Came out 5.4 seconds. Now, watch carefully. Here's their timing. 1 cycle represents 1 second. Okay, that was 5.4 seconds. Hard to see. Let's do it in slow motion backwards. So you'll see this building coming back up. And what I'd like you to figure out is where should they have started the clock? At what point is it all the way to where you could justifiably say that's when the downward motion began? How about now? That's when they started their clock. You want to see it again? This is amazing. I'm just taking their data. I went to their stopping point, went back 5.4 seconds, and figure out where they started their clock. Look at that. Would you like them timing your kid at a track meet? I don't think so. Okay, how in the world could they get away with that kind of a fraudulent timing? Now keep in mind, remember that formula they used? Assumes uniform acceleration. Even if you say that once it starts moving downward, it's uniformly accelerating, it needs to be a priori. It needs to be, like you drop a soccer ball, you have a priori a pretty good sense that it's going to come down at uniform acceleration, except for air resistance and stuff. But for the building, a complicated thing like that, you can't assume anything. And so for them to use a formula that assumes it's a simple dropping a tennis ball or dropping a golf ball or something like that, and assume that that's going to apply, and then apply it to this interval of time where it's obviously not uniform because it sat there for 1.5 seconds before it even started to really move. The equation NIST used is invalid unless the motion is known a priori to be uniform acceleration. The timing you just saw does not mark out an interval of uniform motion. NIST used a bad camera angle to get their starting time. Now, here's their camera angle. Notice that it's looking at the Building 7 from the street level, looking up at an angle. And they describe, in fact, John Gross describes verbally as well as it's described in the report, that how they got the starting point for their measurement is they took that roof line, and as soon as a single pixel near the middle, they said as soon as that single pixel turned from building to sky, he's assuming it did that, you see, then they use that as the starting point. But something's going on here. See that little kink in the roof line? That's not a downward kink. This is about the same time in the fall of the building as seen from a camera looking level with the roof line, and you don't see any kink. How could you see zero kink from a level perspective and yet see what looks like a V-shaped kink from below? It's folded laterally, not folded downward. So it's not a downward kink in the roof line, it's a lateral fold in the wall of the building that gives them that V-shaped appearance when seen from this angle. Okay? So they are using bad observational practice to determine when the motion of the building started downward. They're trying to measure downward motion. When I was in junior high, we had a science teacher who put in for a grant. We had a weather station. And so various students could get little licenses and so forth to run the weather station. I became the head weather station operator. And one of the things I learned how to do was go out and take daily readings of all these instruments, including a mercury barometer. And they taught you, you look with your eye level with the top of the mercury so you don't introduce parallax and get bad readings. You see what I'm saying? What are they doing? They're looking at it this way. You have to look, if you want to say when is it coming down, you have to look level with the roof line or you're going to get a bad reading. Do you think the guys at NIST know this? I'm absolutely sure the people at NIST know how to take a good reading with an instrument. You want to eliminate parallax. But what did they do? They have all of these same videos. I didn't introduce, I got these from NIST. We had a FOIA, F-O-I-A, Freedom of Information Act. We got a whole bunch of videos released. That's where these come from. So what we have, they actually have all of these videos cataloged. That's why they say camera 3. I don't remember what number this is, maybe 4 or 5 or something like that. But they have all of these different camera angles of this building cataloged in their report. And yet, they use camera 3 to do their measurement. So it's a bad measurement. They did it intentionally. I call that fraudulent, but that's what they did. Okay, therefore the kink had to be a lateral fold, not a vertical dip. Yet NIST treats the development of this kink as the start of downward motion. That's how they got that extra 1.5 seconds that they threw into the measurement. Now, here's where I said I was going to show you later. That's the size of the footprint of WTC7 on a football field. It overlaps into the end zone. It's roughly the size of a football field. Okay? In other words, it's a huge building. And for this building to come straight down with a level roof line, what does that tell you? What? Well, let's take it in small steps. What it's telling you is all of those vertical supports, all those columns throughout the building had to fail simultaneously. If they failed over here before over here, it's going to come tumbling down, right? So you had to have a synchronized breaking of these columns across the whole width of the building, or this huge, gigantic building here is not going to come straight down as we just saw it did. Okay, here's my measurement. Okay, here I'm tracking the northwest corner of Building 7. This is WTC 7. And I'm tracking this corner because it stays visible all the way down here nicely. I'm also tracking a point here on a stationary object just to see how stable the image is. I'm using this video that's tilted because the camera, this particular camera, they set it up and just let it run, but nobody was tending to it. So nobody was zooming it, moving it, anything. So this is the most stable video shot we have. I can take care of the fact that it's tilted by just changing the coordinate system here. So it's going to treat this line as a vertical line. So we can compensate for the rotation of the image that way. Okay, let's just run it here. And notice I'm tracking this corner and the little mark is going along here on the top here. And then it reaches this point, boom, it starts coming down. And then when it gets to about there, it starts actually slowing down. Here it's increasing its downward speed as this graph comes down, and it literally turns around. So at a certain point, this thing is encountering more resistance and starting to slow down. But as long as this graph is sloped downward, it's picking up downward speed. So let's get a auto fit line here. And look at that. If I use these points to fit the line, the slope of the line is minus 9.81. The acceleration of gravity is 9.8. In fact, in New York City, it varies a little bit from place to place on Earth. In New York City, it's 9.802. So this is as close as these measurements can come. There's a little bit of variation in the data there. And if I chose different points, it would come out slightly different. But it comes out 9.81. So this is essentially as close as this data is good for an absolute free fall. This is coming at the acceleration of gravity. Okay. When I first measured that, it blew me away. So here it's falling with zero resistance, and then it starts encountering resistance as it gets further down here. Ultimately, the top part of the building is going to crush into the bottom part of the building. But for quite a section in here, it's in absolute free fall. Notice from the time it lets go, it's about 10 seconds after we started the clock. From 10, here's 11, here's 12, that's 2 seconds. Here's about 2.5 seconds, 12.5 or so. So 2.5 seconds of free fall. Okay, very interesting. That's about 8 floors worth of free fall. 8 floors, over 100 feet of absolute free fall before it starts encountering any resistance. Okay, so for 8 floors, there was nothing there. A free-falling object cannot do work, if you know the physics definition of work. You can't, if an object is in free fall, all of its energy, all of its potential energy is being converted into downward motion, kinetic energy, nothing left over to do anything else with. It can't be crushing the building because all of its energy got used in simply picking up speed. And so, excuse me, you have a hand up?
Yeah. What happened for the drag? What happened for the drop?
What?
What happened for the drag? For the free fall? You need to also consider the drag. Air resistance.
Yeah, well, if you have a large mass falling through air, air resistance is not very significant. Okay, so the air resistance is not significant in this case. What this is showing is nothing is very significant here. The whole chunk is falling as close as we can measure to absolute free fall. And if you take a ping pong ball and you drop it, air resistance shows up right away, right? Because it's a light mass and a little bit of force due to the air resistance will deflect the motion of the ping pong ball very quickly. I did one earlier before, I guess you guys walked in late. I did one where we dropped a soccer ball. And there, if you actually look down at the bottom end of that graph, if we went back and checked it out again, it deviates from free fall in the very last little bit of the graph. So you can see a little bit of deflection because of air resistance. Okay, but if you dropped a cannonball, you know, the same force applies if it has the same profile plowing through the air. So take a softball and a shot put, say they're the same size, okay? They're going to both encounter the same force because they're displacing the same amount of air, but that force will be more noticeable for the softball and less noticeable for the cannonball, right, or the shot put. So here, yeah, air resistance is not a factor in this kind of measurement. Okay. Yeah. Well, okay, I'm going to save most of my questions, but if it's specific to this, go ahead. Yeah.
Before that, the timeline where it's constant, I would have expected a fully flat line, but I see a little pattern.
Measurement error. I mean, you're talking about a camera that's a long distance away. So the question was, I'm not sure if the mic could pick him up. Okay, he's asking about why the line at the top isn't perfectly smooth. And it's just there's a little bit of noise in the measurement, that's all. At pretty much any physical measurement you do, there's a certain limitation in how much precision you can get. And so one of the things is just turbulence of the air, for instance, between the camera and the building. Like this camera is a telephoto lens up somewhere, I think, near the Empire State Building. So it's a long distance, and just a little bit of ripple in the air would be picked up. I think I mentioned earlier that I tracked another point on a stationary object. just to see how much a stationary object would wobble. And it goes a few inches, you know. It goes around a little bit too, because that's just the inherent noise in the measurement. So yeah, that's why you can't expect physics measurements to be perfectly smooth. Well, maybe, but that's making, I mean, sorta. Okay, I will say, okay, that's an interesting point actually. There were other things going on in the building before. So maybe some of that cyclical part is real. In general, I think it's noise. There might be a slight signal in the noise if there's trembling in the building and things like that. So I do know there was, okay, I didn't pick up on that at first, but yeah, there's potential that we're actually seeing something there, but I haven't investigated that. Okay? Okay. Now, that was my measurement. Actually, this is a remeasurement. I was using cruder tools initially. But in August of 2008, NIST they released their final report for public comment. And they had a technical briefing conference. And so I was on the mailing list for architects and engineers for 9/11 Truth. And they were saying, oh, we're going to have this briefing conference. We ought to get some of our guys to ask questions. So I looked into putting in to ask a question. But then I found out you have to be affiliated with some institution or something, like some university or like a scientific corporation of some sort or whatever. I didn't know. So I thought, well, they're not going to take me. I was just a high school teacher at the time. So, but then at the last minute I thought, what the heck, I'm going to apply. So I applied and I put down American Association of Physics Teachers, which is true. It's a professional organization for physics teachers. And so that was my way of associating myself with some institutional entity, all right? And so this is what happened. I got a password emailed to me about 5 minutes before the conference started. As I was walking out the door to go to school, I checked my email quickly. Boom, here's a password. So I sat down, I tossed off a question. So the question you're going to hear here was composed practically real time. I just typed it out, hit enter, and left for school. I didn't know for weeks whether they even asked it, but it turned out they did, and here's what resulted.
Our next question comes from David Chandler of the American Association of Physics Teachers. Any number of competent measurements using a variety of methods indicate the northwest corner of WTC7 fell with an acceleration within a few percent of the acceleration of gravity. Yet your report contradicts this, claiming 40% slower than free fall based on a single data point. How can such a publicly visible, easily measurable quantity be set aside?
Can you repeat the question, please?
Sure. Any number of measurements using a variety of methods indicate the northwest corner of WTC7 fell with an acceleration within a few percent of the acceleration of gravity. Yet the report contradicts this, claiming 40% slower than the free fall based on a single data point.
Well, first of all, gravity is the loading function that applies to the structure, applies to every body, all bodies on this particular on this planet, not just in ground zero. The analysis showed there's a difference in time between a free fall time. A free fall time would be an object that has no structural components below it. And if you look at the analysis of the video, it shows that the time it takes for the 17 for the roof line of the video to collapse down the 17 floors that you can actually see in the video, below which you can't see anything in the video, is about 3.9 seconds. What the analysis shows, and the structural analysis shows, or the collapse analysis shows, it's that same time that it took for the structural model to come down from the roof line all the way for those 17 floors to disappear is 5.4 seconds. It's but 1.5 seconds or roughly 40% more time for that free fall to happen. And that is not at all unusual, because there was structural resistance that was provided in this particular case, and you had a sequence of structural failures that had to take place, and where everything was not instantaneous.
You asked what NIST said? There you go. Actually, he started off totally disoriented by such a simple question, but then he actually got some traction. And so his real answer, which started about at the halfway point, was, if you look at the videos, the roof line comes down in 3.9 seconds. But our mathematical modeling of this says it ought to be 5.4 seconds. And that makes sense, because free fall only occurs when there's no resistance. But there was resistance here. There was a whole sequence of structural failures that had to take place. And they couldn't all take place at once. So he's arguing that we should accept the 5.4 seconds because it makes sense, and that's what their model predicts. But he's pushing aside the actual observational data that it came down at absolute free fall, together with the fact that they're still not measuring this in a valid way. They're taking a starting time and an ending time. And so it's sort of like, you know, that graph that you saw going horizontally for a while and then down? Okay? So it's like if I took the first point on that graph, and then I took the last point on that graph and did a straight line between them, that's going to be there 40% less than free fall. So it's like ignoring all of the actual motion of the building. They're taking the starting and ending points, ignoring what happens in between, and characterizing the motion that way, which is something that I wouldn't give credit for in a high school physics class. Because if you're going to take a complicated motion and talk about the acceleration of an object, you have to graph the velocity versus time and find the slope of the tangent line, and that's how you get the acceleration, to see whether the acceleration changes or whatever is going on. But they're ignoring all the data except 2 points, starting and ending. So now, this is not the end. There was another guy in our group, Stephen Jones, who asked a question that I considered so trivial, I was sort of almost embarrassed that he even asked it. It's, well, that's just a typo. Well, it wasn't a typo, it was what I call a conceptual typo. They used the wrong word, which has a wrong concept attached, okay? But let's see what that is. So here's Stephen Jones's question.
This next question comes from Dr. Stephen Jones. NIST discusses the fall time for WTC7 on page 40 of the summary report, where it's stated, assuming that the descent speed was approximately constant. However, observations by others of the descent speed show that the building is accelerating rather than being at constant speed. So the question is, why did NIST assume that the descent speed was approximately constant?
Well, I'm going to have John Gross answer that question as soon as he's ready, but the most important thing is this was a gravitational force, so gravitation is a force of acceleration. So I will have John clarify what we said.
Yeah, the force of gravity obviously is the acceleration of gravity is what's at the driving force, and our calculation was based on the amount of time from the top of the parapet to fall till it disappeared from view between the two buildings seen in the video. That time was established from the video by single frame search of the time, so that was down to 1/30th of a second. And then we did the same thing for when the top of the parapet disappeared. We found that time to be 5.4 seconds.
So, Steve, can you repeat that question? What is it that is being asked here?
Let me go back to it. The question was, why did we report descent speed rather than acceleration? The statements in the report has to do with assuming that the descent speed is constant.
Well, the descent speed is not constant. Obviously, it goes from 0 at the initial to a later speed. We computed the time that it takes to drop the roughly 18 stories that were in view. We also provided a calculation based on the distance from the top of the parapet to the lowest point visible to compare that with the free fall speed.
So I guess, is there a sentence there that
Yes,
explicitly,
let me-
what does the sentence mean? Fahim, can you clarify that?
I think it's something that we need to clarify and correct in the final version of the report.
Okay. Thank you for pointing that out to us, because that probably needs fixing.
So they used a simple, I thought it was just the equivalent of a typo. They said speed, they meant to say acceleration. They should have said, whoops, we'll fix that. But I didn't hear a whoops anywhere in there. And it's like they went around for 40, I mean, John Gross, I timed it, 45 seconds saying nothing in response to that. So what's going on with NIST that they're responding in this kind of a way to something which is a direct, publicly visible, easily measurable thing, as I was phrasing it earlier? Anybody with the competence of a high school physics teacher, and there's a fair number of us in this country, not everybody has that kind of background, but there's a whole lot of people who do, and a lot of physics students would be able to follow every single bit of the physics involved here, and yet they're dancing around and not answering the questions and so forth. However, the significant thing in this interchange with Stephen Jones is they committed to making a change in the final report. With my earlier thing, they danced around it, never going anywhere, and dropped it. But here they actually committed on video to change the final report. Okay. So to summarize, they came up with this measurement using an invalid method, bad data because of a bad camera angle. NIST knew, by the way, NIST knew that that was a lateral fold because they mentioned that elsewhere in the report. That wasn't just something we discovered. They knew it, and yet they were treating it as though, and they used a camera angle that would be deceptive, that would make it ambiguous so that they could claim that that lateral fold was a vertical dip so that they could get the measurement that they were trying to get. So they're clearly falsifying data to get a predetermined result. But they couldn't admit free fall because free fall is when there is no support. And in this case, there was support. And many failures had to take place, and they couldn't all happen at once, as Shamsunder said, right? So that's why they couldn't admit that Building 7 came down at free fall. Okay, so but they committed to make a change. And so, by the way, if you keep the dates in mind, there's some politics here. August 2008 is still during the Bush administration. They came out with their final report in November of 2008 after the election. So we're now into the lame duck period. Obama has been elected, but Bush is still president. And during that interval is when they released their final report and walked away from it. In the final report, here's what they actually do. They claim that their original measurement is still valid. So that answers your question. They're claiming this original measurement with the bad camera angle that's deceptive and all that kind of thing, and this formula that only applies for uniform acceleration, but it's not uniform. They're claiming all of that's still valid, but then they offered a second analysis for more detail, and the second analysis contradicts the original, and it actually acknowledges free fall. And then they continue to use camera 3 for their final analysis. Here's the graph they produced. Okay? Now, this was their sort of enhanced version of their analysis. They're still claiming the original analysis is valid, but notice that that's the stage 1, stage 2, and stage 3. If you take them all together, you get 5.4 seconds. That's their 5.4 seconds. And so to get 5.4 seconds, you have to start way back here when the building is not moving vertically. This entire stage 1 is phony. That entire stage 1 is due to the artifact of using the deceptive camera angle. That's the lateral movement of the building that they're lumping in with vertical motion. And so the real issue is, see that red line in there? There's the equation of the line. V of t is 44.773 plus 32.196 t. That 32.196 in feet per second squared, not metric units, that's the acceleration of gravity. This red line, they put it right there in the graph, is an indication of absolute free fall. They claim it for 2.25 seconds. That's because they chop off this little corner back here. You saw a perfectly decent measurement a few minutes ago that was 2.5 seconds. That extra quarter second is because they're phonying up this first part data. But still, 2.25 seconds even, give it to them. That has all the same implications of what I'm saying, is that if it's in free fall, there's zero resistance for over 100 feet for 8 floors. And here is their final conclusion. As noted above, the collapse time was approximately, see, they're quoting the original here. As noted above, the collapse time was approximately 40% longer than that of free fall for the first 18 stories of descent. The detailed analysis shows that this increase in time is due primarily to stage 1, entirely phony. The 3 stages of collapse progression described above are consistent with the results of the global collapse analysis discussed in chapter 12, blah, blah, blah. It's not consistent with anything, okay? And I went back and read that, chapter 12, okay? It's not consistent with that, okay? So here we have NIST lying and continuing to lie. Someone at NIST, however, put that bright red regression line through their stage 2 data and put the equation of the line in there with the slope of that line for everybody to read. It shows absolute free fall. So the wording of their conclusion still denies free fall, and yet there it is for the world to see with a red line. So it tells me somebody at NIST is trying to blow a whistle. If you're here tonight, contact nisterrors.com, a site to assist whistleblowers. We have a lawyer who specializes in whistleblowers. So conclusions. Free fall of WTC 7 and the near free fall of WTC 1, North Tower, imply the use of explosives, which implies preparation and foreknowledge. If you're going to have explosives pre-planted, ready for the date of 9/11, it had to be coordinated with the events of 9/11. It had to be by people capable of orchestrating a coordinated operation involving access to the buildings, access to military explosives. Nanothermite, which was found in the dust, is not on the commercial market. It's a military material, manufactured at military labs like Lawrence Livermore and a few others. It requires demolition expertise. By the way, I had a friend who was in the demolitions in the military, and he said, I was talking about demolition, controlled demolition and all that. He said, hey, the world's most experienced demolition experts are in the U.S. Army. Okay, so that's another thing to throw in. This is not necessarily, people think of civilian demolitions, but there's other places where this expertise exists. The ability to choreograph the activities of the hijackers. We had hijackers. They came into this country on phony baloney visas, most of them through a single embassy, or I'm not sure, consulate or whatever it was in Arabia, Regia, I believe it was, through one guy. So this, you had to coordinate with the State Department to get these guys into the country. The FBI was tracking them around the whole time they were here. They were not just unknowns from nowhere. We were following them. So who's pulling off 9/11? It takes these elements, okay? So rather than just make an accusation, I'm just saying we can place constraints on who the perpetrators have to be. They have to have access to the buildings, access to military explosive. They have to have demolition expertise, the ability to choreograph activities of the hijackers, which involves either the CIA or State Department, the ability to stand down the military response to make sure the planes got to their targets, the ability to control the media, to control the message afterwards, clean up the mess in that regard. By the way, have to have the ability to override every principle of investigation to ship all this steel off to China and melt it down, rather than keep this as forensic evidence. Nobody had an opportunity to analyze the steel. There were a few pieces of steel selected out, and that's all they kept. But all of that should have been treated as forensic material. And they had to have the ability to orchestrate a corrupt NIST report. Like, that's big. NIST has a reputation that they're willing to muddy up with this horrendous report that I, a mere high school teacher, if you want to look at it that way, I mean, I've showed you a whole bunch of holes. I've showed you the guys that are writing this report. This was a mess. And who's causing them to do that? Well, this is a branch of the executive, and so it basically shows arrows pointing up the chain in the executive department, in the executive branch of government. So the administration is culpable. Military-industrial complex at some level, whether it's the military, whether it's the contractors, whoever it is, they're culpable. The CIA, State Department, whoever, I mean, a lot of these people are maybe independent of each other. Only a few people maybe get the whole picture. That's the way they do things. But we're looking at those kinds of people and the physics of it, just taking free fall, one piece of evidence that points to all of these conclusions. So I will lead you to that. Lead you with that is we need a real investigation. And here's my website, 911speakout.org. All of my research is there. Colorado911truth.org is the local organization. If you want to become more active, see them.